Hello students, today we will discuss about extinction. The minerals become extinct as we rotate the stage of the microscope through an angle of 360 degree 4 times at 90 degree interval. So how it occurs, why it occurs, and whether the extinction is a feature that is found in all minerals or in anisotropic minerals, all those features that will be discussed. So it is one of the important property of minerals studied in cross-nickel condition of the petrological microscope. So extinction, it is a property which can be studied in cross-nickel condition, not in plain polarized light but through cross-nickel condition by using polarized light in orthoscopy arrangement. So it takes place when the vibration direction of the mineral section coincides with the vibration direction of the nickels or polars. So when extinction will take place? When the vibration direction of the mineral section coincides with the vibration direction of the nickels. In that condition only, no light reaches the eyepiece and there occurs total darkness. So this is the position of extinction. Here, in order to know why extinction occurs, we should remember that every mineral section has got two fixed directions of vibration along which light always vibrates and is transmitted. So every mineral section, any mineral section you take, it will present the vibration direction which is fixed for that mineral section. If it is like this, everywhere it will be like this. Everywhere it will be like this. That is fixed. So these two directions are mutually perpendicular. And when you talk about the cross condition of the microscope, the analyzer and polarizer, their vibration direction are mutually perpendicular. So in that condition only we say they are crossed. So this will indicate the analyzer and polarizer vibration direction, and every mineral section will have two vibration directions which will be mutually perpendicular. So as you rotate the stage of the microscope through an angle of 360 degree, or you can say that angle. So by rotating the stage of the microscope through 360 degree, the vibration direction of the mineral section, this will match with this polarizer and analyzer vibration directions 4 times. And when this occurs, matching occurs, the mineral will become extinct. So in order to study the extinction position of the mineral, we see that the vibration direction of the mineral section coincides with the vibration direction of nickels, and in that condition darkness results, and that is the position of extinction. So these two directions are mutually perpendicular to each other. The mineral vibration direction, similarly the vibration direction of the polars, when the vibration direction of minerals and that of the polars are parallel, no light passes through and there occurs darkness. This is the state of extinction. At the stage the microscope is rotated, the vibration direction of the mineral section will match with the polar vibration direction 4 times at 90 degree interval through the rotation of the stage by an angle of 360 degree. That's why it is said that a mineral section will exhibit the extinction position 4 times as you rotate the stage of the microscope through an angle of 360 degree. Let us look at the following figure. So this is the mineral section, and as I have told, every section has got two fixed directions of vibration. So this is the direction of vibration fixed for this mineral section. And these are mutually perpendicular. One of this direction will become fast, the other will become slow. If it becomes slow, fast, it will become slow. Or if it is the direction of E ray, it will become the direction of O ray. So these things you have to remember. So the vibration directions of the mineral will either represent O ray or E ray, or it will represent fast ray or slow ray. The term fast ray and slow ray is generally used in case of axial minerals, and the term fast O ray, E ray, that is used in case of uniaxial minerals. And this is the condition now. This is the stage of the microscope. These are the polarizer and analyzer vibration directions. This is PP, polarized vibration direction. This is AA, this is analyzer vibration direction. They are mutually perpendicular. And here is the mineral section. And if the mineral section will have vibration direction like this, so it is matching with the polar directions. In that case, no light will pass through, and the mineral will show extinction. So the big cross on the stage, actually the marking at the eyepiece of the microscope, this indicates the vibration direction of the polars or nickel prisms. In above diagram, it has been shown that the vibration direction of mineral has been parallel to the vibration direction of the nickels. Hence, it is the condition of extinction, no light passes through the analyzer, there occurs total darkness, or it is the position of extinction. Now let us have the explanation of this extinction phenomenon. The polarized light from the polarizer comes up to pass through the mineral. The mineral is on the stage, and light coming from the polarizer is vibrating. Let us say it is vibrating parallel to north south, and it will come up. It will come up with vibrations taking place parallel to north south, and it will hit the mineral on the stage. If one of the vibration direction of the mineral is parallel to this direction, then this vibration will simply pass through the mineral with no component parallel to this direction. This happens. So this light gets doubly refracted into two rays, one being the ordinary, the other being extraordinary, or one is the fast ray, other is slow ray. Because as you know, when a ray of light enters into any anisotropic substance, it suffers double refraction. And the two doubly refracted rays vibrate on two mutually perpendicular planes. But this doesn't happen when the polarized ray coming from the polarizer entering into the mineral section finds one of the vibration direction of the mineral section parallel to the vibration direction of the polarizer. In that case, light simply passes through the mineral with no component vibration perpendicular to that. And this light, when it enters into the analyzer does not allow that light, because analyzer vibration direction is east to west, polarizer vibration direction is north south. So the light that has passed from the polarizer like this, vibrating like this, enters into the mineral section, and it finds that mineral vibration direction is also like this, so it will simply pass through with no component vibration along this direction of the mineral, and light vibrating like this, it will come up and it will meet the analyzer whose vibration direction is like this. So it will hit it perpendicularly. So this vibration will not be allowed along the analyzer vibration direction. So no light will pass through, it will be condition of darkness. So analyzer only allows that light which vibrates oblique to it or parallel to it. So in these two conditions, light can be allowed through the analyzer. So as here in this case it is perpendicular to the analyzer vibration direction, this light cannot be allowed to pass through and darkness results. So this is the reason why the mineral is showing darkness. So if the mineral is showing double refraction, in that case the vibration coming from the polarizer has been split up into two rays. In that case, they do not show parallelism to the vibration direction of the polars. So let us see what are the cases that can arise when we rotate the stage of the microscope through an angle of 360 degrees by keeping the mineral section on the stage. Here are the situation. The vibration direction of the polarizer may be parallel to one of the vibration direction of the mineral section. So here what happens? Here the light simply passes through the mineral section without having any component vibration perpendicular to it. Let us say it is east-west. Because light coming from the polarizer is vibrating like this. It is north-south. So it will simply pass through the mineral and there will be no component along east-west direction. This light passes upwards into the analyzer or upper nickel where the vibration direction is east-west. It will not, or the analyzer will not allow this north-south vibrating light coming from the mineral section to pass through it. Hence, darkness results. The mineral is said to be in the state of extinction. Situation 2. From that position, if the stage is rotated 90 degree, the other vibration direction of the mineral section will become parallel to the polarizer vibration direction. And that is north-south. So, the same situation will arise as it took place in this stage. So, no light will pass through the polarizer, no light will pass through the analyzer, and the mineral will show darkness. It is a case of extinction. And as mineral sections vibration direction mutually perpendicular, polar directions are mutually perpendicular. So when this is rotated, it will match with this 4 times. That's why when you rotate the stage by 360 degree, the vibration direction of the mineral section will coincide with the polar vibration direction 4 times, and in those conditions there will be darkness or extinction, and therefore it is said that the mineral sections display the extinction position 4 times as you rotate the stage of the microscope through an angle of 360 degree. When the vibration direction of the mineral section is not parallel to that of the polars or to that of the polarizer, there the double refraction takes place. And in that condition we will get the interference color. Interference color. So, a mineral shows extinction and interference color as we see them under cross-nickel condition. The interference color is seen except the position of extinction. So, when the vibration direction of the mineral section is not parallel to the polar vibration direction, in that condition we see interference color. Let us say it is like this. This is the vibration direction mineral section, this is the vibration polars. So in this condition there will be darkness. There will be color, and that color will be the interference color. So a mineral goes to position of extinction except the positions of interference color. Or we can say the mineral shows interference color except the positions of extinction. So this phenomenon of extinction is found in case of anisotropy minerals or minerals crystallizing in non-cubic systems. And if we take any section which is cut perpendicular to optic axis of uniaxial or biaxial minerals, in that case also there occurs complete darkness throughout the rotation of the stage. And in that case we said the mineral is in the position of, or the mineral is showing isotropism. This case happens in case of all minerals which crystallize in cubic systems. So cubic systems, the minerals of cubic system are said to be isotropic because light vibrates with equal velocity in all directions, and the light that is coming from the polarizer is not split up into two rays through double refraction. If it is coming parallel to north-south of the microscope from the polarizer, it will simply pass through in that direction through the mineral section, and it will hit the analyzer perpendicularly, so it will not be allowed. Even if the stage is rotated, the same situation will prevail, and therefore the mineral section will show complete darkness, and it is a state of isotropism. So isotropism is seen by the minerals which crystallize in cubic systems or the mineral sections which are cut perpendicular to optic axis. Now we will discuss about the different types of extinction. To know the type of extinction, the crystallographic direction of mineral section or state boundary of the mineral or cleavage of the mineral is compared with the vibration direction of the mineral section in order to identify the type of extinction. So, a mineral section must present straight boundary or cleavages or direction of elongation. And this feature is being coupled with the vibration direction of the mineral section. Based upon this, the type of extinction is being determined. And the different types of extinction are, one of them is parallel extinction, one of them is parallel or straight extinction. So this is the situation. The mineral is mineral section, this is the polar directions, this is the mineral direction, mineral vibration direction, this is the mineral, and if this is the vibration direction is like this, so this is the position of darkness because this is matching with the polar directions. But when you talk about parallel or straight extinction, in that case the cleavages of the mineral must be parallel to any one of the vibration directions. So this cleavage direction is parallel to this vibration direction of the mineral section. So here, so in this condition the mineral is showing darkness. So this is the position of extinction. And in this condition, the cleavages are running parallel to, this is the cleavage direction, it is running parallel to this direction. Cleavages, straight boundaries, direction of elongation, they are said to be the crystallographic direction. So crystallographic direction and the polar direction they match, and the mineral shows darkness. This type of extinction is called straight extinction, and here the extinction angle is 0. The mineral is said to display straight extinction when the mineral placed in the position of extinction presents one of its vibration direction parallel to the cleavage or straight boundary. So this is, so here the extinction angle is 0. Now let us come to the second type of extinction, that is inclined or oblique extinction. So here, when the mineral section is being observed in cross-nickel condition, the vibration direction and the cleavage, they do not match. So vibration direction is like this, cleavages are like this. So the mineral is placed in the position of extinction, that is, the vibration direction mineral section is parallel to the polar directions. Then the stage is rotated to find out the angle between the cleavage and the polar direction, or this direction, either this direction or this direction, this angle or this angle. That will give you the extinction angle. Here, this is the cleavage direction, this is the polar direction. So this angle, if this angle is 30, this angle will be 60. So here, when the vibration direction of the mineral section does not match with the crystallographic directions indicated by cleavages or straight boundaries or direction of elongation, in that case the mineral is said to display the phenomenon of oblique extinction or inclined extinction. In that case, the angle is being measured. The angle, so in one case when the angle is 30, the other case it will be 60. So the general rule is that we have to take the smaller angle. In order to remove the ambiguity, a smaller angle is generally taken. Otherwise, the nature of vibration we will have to determine, because as I have already discussed, one of these direction will be fast, the other direction will be slow. If this is the cleavage direction, then this angle is, if it is 40, this angle will be 50. So angle with fast it is 50, angle with slow it is 40. If we are measuring the fast or slow vibration direction, then we will write down the cleavage angle, we will write down the extinction angle with respect to the vibration directions. Either here it will be 50 for fast, 60 with slow, 40 with slow. Otherwise, if you are not measuring the fast or slow vibration direction of the mineral section, in that case we will take the smaller angle to remove the ambiguity. That's why we take the smaller angle. So this has been explained. This is, if this is the slow, this will be the fast. This will be fast, this is slow. So if slow, with slow it is 30, with fast it will be 60, like this. then symmetrical extinction. Here, a mineral must show cleavages or straight boundaries. Let us say these cleavages are like this. And the vibration direction is found to bisect this angle, cleavage angle. This is the vibration direction. Or we can say the mineral is becoming extinct symmetrical to cleavages. This is the cleavage. These are the cleavages. So this is the vibration direction. So the extinction is taking place symmetrical to cleavages. So in this condition, the vibration direction is like this. Cleavages are like this. Cleavage may be any angle. If this is the cleavage angle, then if the vibration direction is like this, then we say the extinction is taking place symmetrical to cleavage, because if we rotate along this direction, the angle will be same as we rotate in along the other direction. So it is symmetrical extinction, which we generally find in case of calcite and in case of augite. These are the two minerals in which we find symmetrical extinction. Then let us come to the OV or ondulous extinction. This is a case which is seen in case of metamorphic minerals. Metamorphic minerals, or the minerals which have been strained, whose atomic structure has been bent, atomic planes have been bent. So in that case, when the stage is being rotated, all part of the mineral section will not go to extinction at the same time. So it is with rotation of the stage, a curve like body will sweep over the mineral along with the rotation of the stage. Along with the rotation, a curve will sweep, and that is OV or ondulous extinction. It is commonly seen in case of quartz, metamorphic quartz. So on many occasions, the mineral in cross condition do not show extinction completely or uniformly. Rather, different parts of the body goes to extinction on different points of stage rotation, or a wave-like dark band sweeps over the mineral surface during rotation of the stage. This happens when the mineral is found to be deformed, strained, or chemical zoned or twinned. In case of twinned crystals, the extinction angle is not measured because different parts of the twin will show different extinction angle. That's why the twin crystals are not studied through extinction. And OV extinction is commonly found in case of quartz. Extinction with no extinction angle. When the mineral is presenting no such boundary, no straight boundary, no direction of elongation, no cleavage, in that case, the mineral will show extinction, no doubt. Mineral will become dark 4 times as you rotate the stage of the microscope, because every mineral section has 2 directions of vibration and they will match with the polar direction 4 times. But we cannot describe the type of extinction angle in that case. So in order to know the type of extinction angle, the mineral must present crystallographic directions, which are indicated by straight boundaries, cleavages, or by the direction of elongation. That's why in those cases where these features are absent, we do not determine the extinction angle, or we can say extinction taking place without any extinction angle. and let us know which mineral sections or which crystal systems show extinction perfectly, which sections generally show straight extinction, which show oblique extinction. That there is some rule that we should know. All minerals of cubic system, they are isotropic. That means throughout the rotation of the stage they remain dark, totally dark. The mineral is totally dark because it is a mineral which crystallizes in cubic system. Similarly, the sections cut perpendicular to optic axis in case of uniaxial minerals, they will become totally dark under cross Nichols. So basal sections are isotropic. Vertical sections so in case of tetragonal hexagonal system, the vertical sections they show straight extinction, but basal sections show isotropism. In orthorhombic system, pinacoidal sections show straight extinction. Pinacoidal sections will be 1 dot knot, knot 1, knot 1, knot. These sections parallel to these parallel to these planes, parallel to 1 knot, that will be front pinacoid. Parallel to this is basal pinacoid, front pinacoid, side pinacoid. So those possess straight extinction. Similarly, in monocline system, the section parallel to orthopinacoid and basal pinacoid show straight extinction. So in that case, knot 1, knot. These two sections in case of monocline system they show straight extinction. Others show oblique extinction. Similarly, in orthorhombic system, except pinacoidal section, other sections show oblique extinction. So in case of tricline system, as the three axes are all inclined, and we can never get a condition of matching of the vibration direction mineral section with that of the crystallopic direction. That's why they do not show straight extinction. They all show oblique extinction. So all sections of tricline system show oblique extinction. In case of monocline system, orthopinacoid and basal pinacoid they show straight extinction. In case of orthorhombic system, pinacoidal section shows straight extinction. In case of tetragonal hexagonal systems, vertical sections show straight extinction. Basal sections and sections cut perpendicular optics show isotropism. Cubic system minerals show isotropism. So these are the different systems and how they react to the extinction that I discussed. So this is all about extinction. Thank you.